So, is there any hope for a star that started shell burning like that and started to puff up into a red giant? Well, as it turns out, there may be. There's a way to turn helium, through fusion, into carbon and oxygen, and even to turn carbon into oxygen, and sodium, and neon, and magnesium. And neon can be turned into oxygen and magnesium, and so on, until we get to iron. Iron, it turns out, is a dead end. If a star tries to fuse iron into another element, it doesn't release energy. It actually absorbs energy. And so, like I said, iron is a dead end. But the sun is not going to do most of this. At the end of its life, the sun will, for a brief flash of time, fuse helium to make carbon and oxygen. But this will happen, like I said, in a very quick flash of time. And when it does happen, at the end of the sun's red giant phase, the reason it's happening is that the core is starting to collapse. As shell burning itself stops, the core inside the sun will collapse because gravity is always there, waiting to start that collapse again. And when the core collapses to a certain point, the densities and temperatures inside the core will be high enough for helium to fuse into carbon and oxygen. This takes higher densities and higher temperatures than fusing hydrogen into helium. When it happens, it'll happen very quickly, and it will cause the sun to die. The envelope, the rest of the sun, not just the core, but most of the sun's body will be flung out into space by this huge flash of helium burning. It will be ejected and form what is known as a planetary nebula. Planetary nebula are called planetary because when we first saw them around other stars that had died, we thought they were planets because they're kind of round looking. There are lots of beautiful pictures of them on the website you're going to read this lesson. Anyway, that'll be it for the sun and for any life that might still be left on Earth as that hot plasma rushes past and goes out into the interstellar medium. And what's going to be left of the sun? Well, that core, that hot core that just fused all that helium, is going to be left, and it's called a white dwarf. White because it's so hot that it's not even blue, it's white, and dwarf because it's very small. And it's not even really a star anymore. There's no fusion happening there, and it will just slowly cool and fade. And if we want to have life as we know it, we're going to need a new star for that to happen. Alright, so other stars, besides the sun, they're massive enough that they can actually go through many cycles like this of expansion and contraction, fusing one element into another, until they get to iron. And in fact, we're going to talk about that more in just a minute. So let's look at what happens when one of these massive stars decides to finally die. What happens when it has a big core of iron? Well, that iron core is not going to be able to fuse no matter how much pressure we put on it, and so it's going to start to collapse. Once again, the silent assassin, gravity, is there waiting, and it starts to cause that iron core to collapse under its own weight. It collapses so much that protons and electrons are forced to get together to form neutrons. There will be no more protons and electrons. There will only be neutrons. And in the process, some crazy particles called neutrinos are released that carry out tons of energy. When this iron core collapses in this way to form just a big ball of neutrons, it forms a neutron star. A neutron star is essentially one gigantic nucleus. It could be tens or hundreds of kilometers across, like the nucleus of a giant atom. Very, very dense indeed. Much denser than anything you've ever experienced. So dense that it would crush you into a little nothing if you got anywhere near it. Anyway, this neutron star, as it collapses very quickly, leaves a big hole above it. And so all the other layers of the star fall down onto it. And when they hit it, they bounce. Because the neutron star is very hard, the rest of this star falls down, hits this neutron star core, and bounces off. The energy in light and heat and neutrinos that is released in this situation is equivalent to 100 billion stars, the power of an entire galaxy unleashed for just a few seconds. And this is what we call a supernova explosion, one of the most dramatic things that we know of that happens in the universe. And this is how big stars die. They form neutron stars in their cores, and the rest of the envelope is blown apart and recycled back into the interstellar medium in the form of a supernova. These things are terrible and beautiful, and we've seen some of them from here. Fortunately, they've not been close enough to destroy us, but we've seen what they've done to other parts of the galaxy. Just a final word about stellar evolution. It's actually really important to you and to me. This cosmic recycling of elements every time a star dies, it's a cycle that continues again and again. Our star was formed from the recycled elements from the ejected gas envelope of other stars that came before our star. Either they were small stars like our Sun that ended up throwing out their envelopes in a planetary nebula, or there were big stars that exploded in supernovae and released their elements that way. In fact, it must have been some of both. The stardust that formed our star also formed our planet. It also formed you. The atoms in your body came from the interiors of previous generations of stars. Now, how do I know that? Well, it has been shown that the Big Bang at the beginning of the universe produced helium, hydrogen, and some lithium. All the other elements heavier than that were formed by stars. It's the only way we know that this could have happened. In fact, the elements of boron all the way through iron can be formed inside a main sequence star's core as it fuses these elements together. But as I explained, beyond iron, fusion is not an efficient process. It doesn't happen in the cores of stars during their normal lifetime. And to get elements heavier than iron, starting with cobalt all the way out to the heaviest element I know of, number 118, that doesn't even have a real name yet, to get those elements, you need a supernova. In that titanic explosion that is a supernova, forces are released that are so great that even though it requires a lot of energy, elements like iron are fused together to form other elements. This is where, if you have any gold or silver jewelry, that gold and silver was formed in an exploding star, in a supernova. The radioactive uranium and potassium inside the center of our Earth was probably formed in supernova explosions, and it's this radioactive material that produces the heat that causes the Earth to remain molten and have a plate tectonic system. So, many of the atoms in your body came from the centers of living or dying stars, and so as the great scientist and entertainer Carl Sagan once said, we are all stardust. And I think that's a beautiful way to end this lecture. Please proceed to the online websites and try to work your way through that stuff and answer the questions. Good luck, guys, and don't hesitate to email me with questions. Have a good day.